Bismillahirrahmanirrahim. Hello everyone, I hope you are all doing well. My name is Azmat Ali and I welcome you all in the class of Real Analysis by Robert G. Bartle. Lastly, we have discussed up to question number 22 of problem exercise 2.1, chapter number 2. In today's lecture, we will start from question number 23 and inshallah we will cover the complete exercise. Question number 23. It is given that if A and B are positive integers, positive real number, and n is an integer, then we have to show if A is less than B. This is possible if and only if A raised to power n is less than B raised to power n. So, suppose A is less than B, and by mathematical induction we show that A raised to power n is less than B raised to power n. The given condition, given question has two conditions. Firstly, we suppose A is less than B, then we will show that A raised to power n is less than B raised to power n. And conversely, we will suppose A raised to power n is less than B raised to power n, then we will show A is less than B. So, start from A less than B and we will show A raised to power n is less than B raised to power n by using mathematical induction. So, when n is equal to 1, when you put here n is equal to 1, this is A raised to power n less than B raised to power n, that is A less than B. It is true by supposition, because in supposition it is given that A is less than B here. Suppose that statement is true for n is equal to k, that is A raised to power k is less than B raised to power k. Say this is inequality number 1. We show that statement is also true for n is equal to k plus 1. That is, we will show that n is A raised to power k plus 1 is less than B raised to power k plus 1. Multiply 1 both sides by A greater than 0. It is given that A and B both are positive real number. So that's why I am writing here A is greater than 0. So when we multiply a positive inequality number 1 with a positive real number, the sign of inequality will not affect it. So this becomes A into A raised to power k less than A raised into B raised to power k. Now A into A raised to power k is A raised to power k plus 1 and this is A into B raised to power k. Say this is inequality number 2. Again it is given that A is less than B. Now multiply on both sides by B raised to power k. This becomes AB whole power k less than B raised to power k plus 1. Say this is inequality number 3. Combining 2 and 3, we have by using transitive property A raised to power k plus 1 less than A raised to power B, A into B raised to power k, and A into B raised to power k is less than B raised to power k plus 1. Hence, A raised to power k plus 1 is less than B raised to power k plus 1. And finally, by induction, statement is true for every positive integer. Now, conversely, we suppose that for a fixed n belong to n, A raised to power n is less than B raised to power n, and we will show that A is less than B. Here we cannot write the statement is true for all n belong to n. Actually, we will fix any positive integer like I say whenever A square is less than B square. This is true when A is less than B. I say A raised to power 10 whenever A raised to power 10 is less than B raised to power 10, then A is less than B. So at the same time I will fix any one positive integer, and then I will show that this statement is true whenever this statement is true, then A less than B. To prove, we use the contradiction. We suppose that A raised to power n is less than B raised to power n. This part is true, but A is not less than B. If A is not less than B, then it means A is greater than or equal to B. So this statement has this expression has two cases. A greater than or equal to B means A is greater than B, or A is equal to B, or A is greater than B. If A is equal to B, then taking power n on both sides, this becomes A raised to power n equal to B raised to power n. But this leads to the contradiction that a raised to power n is less than b raised to power n, because here we suppose that a raised to power n is less than a raised to power n is less than b raised to power n. This is true only when a is less than b. But if we choose a and b both are equal, then by this supposition we cannot prove a raised to power n less than b raised to power n. Case number 2, if a is greater than b, this means b is less than a. So using the first part of this question, which says at a smaller number the exponent is smaller, so when you take n on both sides here, this becomes b raised to power n is less than a raised to power n. This again leads to the contradiction, because we have to show that we have supposed that a raised to power n is less than b raised to power n, but this is b raised to power n is less than a raised to power n. So this again leads to the contradiction that a raised to power n is less than b raised to power n. Hence, from both cases, for some fixed positive integer n, a raised to power n is less than b raised to power n, then a raised to power a is less than b. Next, question number 24a. Next, question number 24a. This question has two parts. In the first part, if c is greater than 1, this is c is any real number, and m and n are positive integer, we have to show that c raised to power m is greater than c raised to power n. If and only if m is greater than n, that is the exponent at a higher number gives the greater result. Given c is greater than 1, m and n both are in positive integer, we suppose that m is greater than n, and we show c raised to power m is greater than c raised to power n. Since m is greater than n and m and n both are the positive integer, so clearly m can be written as n plus k. Suppose my m is 10 and my n is 3, then m is greater than n here. Now you can write 10 is equal to 3 plus k is here 7. So the larger number can be written as sum of the two positive integer n plus k. So c raised to power m is equal to c raised to power n plus k by substituting m is equal to n plus k. By using the law of exponent, I can write it as c raised to power n into c raised to power k. This is my equation number 1. As c is greater than 1 and k is positive integer, this implies that c raised to power k is always greater than c, and c is greater than 1, it is given. This is done by problem 22a. In problem number 22a, we have proved that if c is greater than 1 and k is any positive integer, then always c raised to power k is greater than c, and c is greater than 1, it is given. So inequality number 1 can be written as c raised to power m, replacing c raised to power k as this result says c raised to power k is greater than 1. So replacing c raised to power k with 1 and change equal sign with greater than sign, or in other words, we can do this as c raised to power k is greater than 1, if you multiply on both sides by c raised to power n, where c raised to power n is clearly a positive integer, a positive real number, sorry, this becomes c raised to power n into c raised to power k is greater than c raised to power n. So combining this one with this result, we have c raised to power m is greater than c raised to power n. Conversely, we suppose that for some fixed m and n, c raised to power m greater than c raised to power n, and we will show that m is greater than n. We will use the same scenario here that we discussed in above question. To prove we use the contradiction. We suppose c raised to power m is greater than c raised to power n. This statement is true, but m is not greater than n. M is not greater than n. It means m is less than or equal to n. So again we have a two case: m is equal to n or either m is less than n. When m is equal to n, this implies c raised to power m is equal to c raised to power n, but this leads to the contradiction that c raised to power m is greater than c raised to power n. If m is less than n, then clearly by using the above part, that is at a smaller number, the exponent is smaller. So c raised to power m is less than c raised to power n. This again leads to the contradiction that c raised to power m is greater than c raised to power n. Hence, from both cases, when for some fixed mn positive mn belong to n, c raised to power m is greater than c raised to power n, then we have m greater than n. 24b. I hope you can do this question. In this part, your c lies between 0 to 1 and mn belong to n. In this question, at a higher power where m is greater than n, m is larger than n, at a higher power exponent is smaller. For example, suppose your c is 0.5, your m is 3 and n is 2. Now if you take c square, this becomes 0.25, but if you take c cube, this becomes 0.125. Now you can notice that at a higher exponent, the result is smaller than the lower exponent. So I hope that you can do this question. I am just sharing the answer. You can use the same steps that I have done in above part. So this is the solution. I hope you can see this. Next we discuss question number 25. Okay, next we discuss question number 25. Assuming the existence of root, show that if c is greater than 1, then c raised to power 1 over m, that is the mth root of c, is less than nth root of c, if and only if m is greater than n. Given c is greater than 1, m and are the positive integer, we suppose m is greater than n, and we show that c raised to power 1 over m, that is the mth root of c, is less than nth root of c. As here m is greater than n and c is greater than 1, then by problem 24a that we have discussed above, c raised to power m is always greater than c raised to power n. Say this is inequality number 1. Since root exists by assumption, it is given in the question, root exists. So by taking the 1 over exponent 1 over mn or the mnth root, and it will always a positive number. We have c raised to power m whole power 1 over mn, c raised to power n whole power 1 over mn. By cancelling m from here, we have c raised to power n remaining, and when we cancel n with n, we have c raised to power 1 over m here. Or in other words, c raised to power 1 over m is less than c raised to power 1 over n, that is required. Conversely, suppose that for some fixed mn belong to capital N, set of a positive integer, c raised to power 1 over m is less than c raised to power 1 over n, and we show that m is greater than n. We will use the same scenario, same strategy that we have discussed in above questions. We prove it by contradiction. Suppose the mth root of c is less than nth root of c, and we will but m is not greater than n. In other words, m is less than or equal to n. So when m is equal to n, then clearly the mth root is equal to the nth root of c, but this leads to the contradiction that c raised to power 1 over m is less than c raised to power 1 over n. Case number 2. If m is less than n, then clearly when you take reciprocal or multiply with mn on both sides, 1 over m on with both sides, we have 1 over n less than 1 over m. This shows 1 over n, this number is less than 1 over m. So at a smaller exponent, this exponent will be less than c raised to power 1 over m. This again leads to the contradiction that c raised to power 1 over m is less than c raised to power 1 over n, because we have supposed that c raised to power 1 over m is less than c raised to power 1 over m. But in both cases, this goes to the contradiction that it is less c raised to power 1 over m is less than c raised to power 1 over n. Hence, from both cases, when for some fixed positive integer c raised to power 1 over m is less than c raised to power 1 over n, we have m is greater than n. Last question of the exercise, question number 26. The statement is, use mathematical induction to show that if a is any real number, m and n are positive integer, then a raised to power m plus n is equal to a raised to power m into a raised to power n, and a raised to power m whole power n is equal to a raised to power mn. You know, these are the law of exponents. Let in this question, as you see here, there are the two positive integer m and n. To solve this question, we will fix one of them. You can fix m and you can fix n. I am fixing m, and when we use mathematical induction for this integer n. Although you can use the mathematical induction for both m and n, and this is called the double variable induction, but this is very complicated. If you use double induction, then at the first step, you will suppose the statement for m is equal to 1 and n is equal to 1. You will check statement for m is equal to 1 and n is equal to 1. At the hypothesis step n is equal to k, you will suppose the statement is true for m is equal to k1 and n is equal to k2. And then at the inductive step, you will prove this statement is true for m is equal to k plus 1 and n is equal to k2 plus 1. But this becomes very complicated. So that's why the best strategy to solve this question, we will fix one of the m or n. So let m is fixed and we use mathematical induction for n. Now the first step of mathematical induction, you know that we will check the statement for n is equal to 1. So when you put here n is equal to 1, we have a is equal to m plus 1, and on the right side when you put n is equal to 1, here we have a raised to power m into a. Now both of the sides are equal. How? If you see here, a raised to power m means this is the m factors, or a is up to m times into a. So collectively, if you combine all of the factors, these are actually m plus 1 factors that represent a raised to power m plus 1. So the statement is true for n is equal to 1 here. For n is equal to k, suppose that the statement is true for n is equal to k, that is a raised to power m plus k. When you put here n is equal to k, this becomes a raised to power m plus k, and when you put n is equal to k here, this becomes a raised to power m into a raised to power k. Say this is star. For n is equal to k plus 1, we show that the statement is true for n is equal to k plus 1, that is we have to show that a raised to power m plus k plus 1 is equal to a raised to power m into a raised to power k plus 1. How can we obtain this expression? In the given question, we have to show a raised to power m plus n is equal to a raised to power m into a raised to power n. So when we replace here n is equal to k plus 1, this becomes the left hand side, and when we put n is equal to k plus 1, this becomes the right hand side. Now I will consider the left hand side and I will show that this is equal to the right hand side. Consider a raised to power m plus k plus 1. We can break this a raised to power m plus k into a using star. Star says this is equal to a raised to power m into a raised to power k, and this is my last a. Now by combining these two factors, we have a raised to power m into a raised to power k plus 1. Last expression shows that the given statement is true for n is equal to k plus 1 whenever it is true for n is equal to k. Hence, by mathematical induction, statement is true for every positive integer. This question has a second part also. A raised to power m whole power n is equal to a raised to power mn. We will also show this result by mathematical induction according to the condition of question number this question. For n is equal to 1, given statement is true. A given statement becomes a raised to power m into 1, a raised to power m into 1. This is simply a raised to power m because any power because at power 1 the base will be same. So this is a raised to power m, and when you multiply m with 1, this is equal to a raised to power m. So both left and right side are equal. So the statement is true for n is equal to 1. For n is equal to k, suppose that the statement is true for n is equal to k, that is a raised to power m whole power k is equal to a raised to power mk. Say this is my star. For n is equal to k plus 1, we show that the statement is true for n is equal to k plus 1. That is, we have to show that a raised to power m whole power k plus 1 can be written as a raised to power mk plus m. Consider the left hand side, a raised to power m whole power k plus 1. We can break this expression a raised to power mk into a raised to power m using star. Star says a raised to power m whole power k is equal to a raised to power mk. Sorry, this is not my star. This is star. A raised to power m whole power k is equal to a raised to power mk. So substituting the value of this is equal to a raised to power mk. Now combining these two factors, we have a raised to power mk plus m. So last expression shows that given statement is true for n is equal to k plus 1 whenever it is true for n is equal to k. Hence, by mathematical induction, given statement is true for every positive integer. So Alhamdulillah, we have completed exercise 2.1. Inshallah, in the next lecture, we will start from the absolute value of function, that is the section 2.2. If you find this video is helpful, kindly like, share and subscribe my channel. See you in the next lecture. Take care. Allah Hafiz.